Hi, welcome back. In this lecture, I want to give you an introduction about the Python multiprocessing module that will allow us to use parallel execution on a multi-core system. In the previous lecture, we looked at some limitation of Python threading model has. The most important one is this global interpreter lock that or GIL that limits the true parallelism on threads. So instead of running in parallel on different cores, what really happens is that we have basically serialized access to only one core. And this is a big limitation. So he has some utility, for instance, I/O bound kind of workloads, but the kind of workloads that we want to parallelize in these cores are not benefiting from Python threading. So what we want to do is really to run multiple tasks concurrently, simultaneously on different cores. So this can be achieved by using the multiprocessing module in Python. The multiprocessing module allows for process-based parallelism. So each task runs independently on its own process and has access to its own memory. Multiprocessing .process class creates and runs separate processes. Processes run concurrently, and like threads might also be joined, must be joined after the execution. So we need to provide a synchronization point at which we ensure that all the calculation from different processes is done. A point is that each process has its own memory space, so it has no shared variable. We will see some mean to share variables across different processes by telling explicitly these memories can be accessed by the different processes. Let's look at the interface to creating and managing processes. This is called the process class with the different methods. The API is very similar to what we've seen before with the threads in Python. So instead of having threads, we have multiprocessing.process. And then we define what is the task that the process need to complete as a function, in this case called worker. So it's the same task than the previous lecture. So just print worker process is running. So the process itself will create a new process. And then we can start our process. And then also we can ensure that the main program waits for the process to have finished with the target task to be completed. So very similar to what we have seen with the threads interface. However, here we are running on processes. So there is they run in parallel. They cannot communicate directly though. As we saw for thread, the real advantage of multiprocessing module is to run multiple processes, each one doing their own task. And as we did for threads, we have the same approach. First, define processes, a number of processes. In this case, we are looking at creating 4 processes. So we have 4 loops here. We create a process defining which task need to be run and which function need to be run as a task. And also we provide the arguments of this function worker as an argument of the process construction itself. After that, we do the append. So we append this process to all the other one, and we start the executing. So they will execute. At a certain point, we want to synchronize all the processes to be at the same time before progressing further. So we use a loop and we join each thread. After that, after the synchronization point, then the code will print. I said that one difficulty sometimes is that we have no direct mean to communicate between one process and the other one, since each one has its own private memory space. So you cannot access the private memory space of the different processes directly. However, the Python multiprocessing module provides a mean to share memory across different processes. This comes with calling the multiprocessing manager method, and this allows us to create a shared data structure. In order to avoid this problem or address this problem or communicate it across different processes, what we do, we create a share memory space across processes, and we will need to call multiprocessing manager. After that, then we need to declare what is this variable that is shared across different processes, and we do that by calling manager.list for sharing the data. So whenever we want to share data between different processes, we create a shared variable, and we need to do two things. First, we need to create a multiprocessing manager object that creates a manager for the share object, and then we call we declare this share, in this case the share list, as a share_list manager.list. And this allows multi-processes to modify the share list. Processes update the share list independently, but changes are preserved. The example that I want to give you to an application of the multiprocessing module is to find the prime number between a certain range. So we are interested in finding the prime numbers, for instance, between 0 and 2 million. So there are much more advanced technique algorithm to finding a prime number. So this is just the super naive, just following the definition. So what we do, we have loops going from the start to the end, in this case from 0 to millions. And what it does is basically checking that if it can be divided by a number of different factors. So we are looping it, right? And then we check if it can be divided. So if the remainder is equal to 0, then we return false. If we never find any number to which this number that we want to check if it's prime is checked against, and the modulo is equal to 0, then it return true. So just a very simple, naive calculation whether a number is a prime number or not. We basically just have a loop and check in a very naive brute force if it's a prime number on that. So this is the serial implementation, so it's using just one core. What we can do if we want to run on different core? Well, one idea would be, for instance, we split these 0 to 2 millions in different range, from 0 to 500,000, 500,000 to 1 million, 1 million to 1,500,000, and 1,500,000 to 2 million. So 4. And then we gave to different processes the calculation within this range. Each one will need then to put the prime numbers in a shared list. So let's see how we can do using the multiprocessing module. So here we define the number of processes that we want to have. So is 4. Is a 4. Then we define the 4 ranges for that we want our task to operate. There is some indentation issue here, so this should be shifted by a certain number, and just to be in line here. So I will fix the slides on Canvas. But what is the next step? Well, first of all, we want to collect all the results from the different processes. Right, so we create a share list across different processes that our processes can fill it in. So we need to do two things. First, we declare the object manager, and then we create a share list by calling manager.list. Then we want to spawn our processes, so we define a certain number of processes, and the procedure is as the following. First, we have a for loops. Each iteration we create and append and start process. So we have a for loop for a number of workers. In this case, is going to be 4. We create the creation process. We need to tell which function is expressing the task that the process need to run. So in this case, is find primes together with arguments of this function. So in this case, the range And also we provided the result, that is the shared list where we're going to add the prime numbers. After we create, we append, and then we start. Then we have a barrier part that is consists of joining all the threads. So we have a for loops, and then each process object is going to call the join methods, basically enforce a synchronization. Our code won't progress until here, until all the process has been reached this point and are completed. And then we calculate what is the total number of primes, and we print it. So in summary, in this lecture, I introduced the multiprocessing process concepts that create separate processes for parallel execution. We saw a method to start, p.start, and to synchronize. So to ensure that progress at our code can happen only after all the processes are finishing. And we do this by a joining process. The mean to communicate between different processes is by using a shared variable, and we saw how to create a shared list to which different processes can write to. The next step, we are going to look at a higher level abstraction used in a multiprocessing module called a pool. And this will allow to have simpler parallel task management without explicitly taking care of all the processes. This is the last slide of this lecture, and talk to you soon.